a little timer at the top now. Okay, so step 1, draw the picture. Okay, now it doesn't have to be super neat, it's just to get an idea of what we're trying to do. So notice the parabola has y squared, not x squared. So you can think of that as just swapping x and y. So instead of having y equals x squared, it's y squared equals 2x. If you swap x and y, instead of it being a smiley face, it's now on the side. Okay, but very straightforward. It's just going to look something like this. Okay, right, because we swapped x and y, so in the picture we have to swap x and y as well. Again, just a very rough picture so that we can see what to do. So this is going to be y squared equals 2x. And we got another bit of information. This point here, 1/4. So let's fill that in. Let's put that in blue. That's going to be somewhere here. Okay. So that's the point. That's the curve. We want to find the point on the curve that is the closest point to that. So we can imagine some number of points on the parabola. Let's put those in pink. Maybe this one over here. And we can look at the distance between those two. So that's going to look something like this. Okay. We can imagine another point somewhere. Let's say over here. We can look at that distance. Maybe another point further down. Let's say over here. And we can imagine this distance. Oh, that's not very straight. That distance there. Okay, so you can pick a bunch of points on the parabola and you can see that the distance is changing. What we want to do is find the specific pink dot that is the closest to the blue dot. In other words, if you want to write this as an optimization problem, we want to find the pink dot that minimizes the distance. That's what it means to be closest. So here we can rephrase this as minimize. Right, we want to maximize or minimize, right? So minimize the distance between the pink dots on the parabola and the fixed blue dot. That one's fixed. We're not changing that. Okay. Now we have it in the form of an optimization problem. And since we're saying minimize the distance, that's the function we want to optimize. It's the distance function. So let's write that out. So let's use d for the distance. This is going to be equal to the square root of x minus 1 squared plus y minus 4 squared. Okay. So this pink dot we're going to call xy. We don't know what that is. It's just some xy. And then the blue dot, that's 1/4. So this is the distance between the two. So again here, blue dot, that is 1/4. And the pink dot, that is xy. Okay. So that's our step 2 done now. We've got the labels. Now we're going to do our step 3, dealing with the function. So we've labeled everything. Now for step 3, dealing with the function. Now here, we can work like this. This is fine with the square root. However, there's a trick we can use to make this slightly easier. Instead of dealing with the square roots of all of that, we're going to square both sides. So instead of minimizing the distance, we're going to minimize the distance squared. So d squared is x minus 1 squared plus y minus 4 squared. Okay. And we'll do some working on the side in a bit to justify this. Okay. So we got our function, the distance squared. It's a little bit easier to work with because we got rid of the root. Okay. Next, we still have this in terms of x and y. We can't work with 2 variables. We want 1 variable. So we can pick one of these to eliminate. Which one would you like to eliminate? You can pick either one. X. Yeah. Y. Okay, let's go with Y. Okay, we're going to eliminate Y. Doesn't matter which one. You get the same answer either way. So let's try eliminate Y. Okay, how do we do that? We use the constraint. What is the constraint for this problem? Exactly. This pink dot over here must be on the parabola. If it must be on the parabola, it must be this form over there. Okay. Now we want to eliminate y, which means in place of y, we're going to put something with x. Okay, so we can take the roots on both sides there. And then substitute it back. That will give us our new function to optimize that is only in terms of x. So let's call that function f. That was our distance squared, and that's going to be equal to x minus 1 squared plus root 2x, which we put in place for y, minus 4 squared. Yeah. Now the question is, optimizing this function, is that different to optimizing this original function with the roots? So this is a different function, right? It looks completely different to that one there. Now, this will give you the same answer as using that one over there, but why? So this function with the roots, if we optimize that one and get a solution, why is that the same as optimizing this function and getting a solution? Think back to what we did yesterday. Yep. No, the derivatives will be very different. This one has 2 squared terms, that one's got a root. So the derivatives will be very different. But why do we get the same answer for both? Okay, let's think back to yesterday. Remember, what was the goal over here? What was the goal to find? The solutions will be a critical point, right? That's what we're looking for. F prime equals 0, we get our x solutions. Those are the critical points. Here, we don't have to worry about this because everything's nice and differentiable. So we're interested in this, f prime at x equals 0. So let's go back to this problem. Okay, so we've got this function. If we do the derivative and set it equal to 0, we get some answers. We look at this function. We do the derivative, set it to 0, get some answers. Why are those the same? Okay, 2 different functions, right? These functions look different, but they give us the same answers. Why?
The same function, but we just split answer.
It's not the same function though. One's got the root, one doesn't have the root. They're going to look different, but something is the same. If I take a function and I square it, there's something that is the same for both. Yeah? Not quite. Okay, let's have a look at a little side example. So let's say we have a very simple function like that. Little parabola, shift it up a bit. Okay, for optimization, what are we interested in? Maximum and the minimum.
Will be the same. But it's still gonna be the same.
Turning point's the same. Yes, well done. You can get some points for that. Let's put your student number there. It's points. Yeah, the turning points are going to be the same. If you have a function like this, over here, there's the turning point. Now, imagine I square this function. Okay, I'm going to square the function now. It's going to look like this. Right, so from x squared, it becomes x to the 4. Right, we've dealt with those before. It's going to look like this. What happens to the turning point? Stay the same. Yeah, the function looks different, but if you find the turning points of the original function and the turning points of the new function, they're exactly the same. And that's what we're looking for. So the turning points or in general, the critical points, if it's not differentiable, are the same for d and d squared. Okay. So if you have some function with the root and you calculate the turning points, it's the exact same as if you calculated the turning points for the square of that function. Okay. So you can look at this picture here. These turning points do not change. Okay. And we can see some more examples. Let's just see if the Wi-Fi is working. Okay, no, it's not. We'll have to look at that another time. But you can look on Desmos, you know how to use that. Put some cubic functions. You know, you got your local min, local max, put some cubic functions, square them, and look at the turning points. You'll see that they'll be the same. Okay, so that is the reason why we can do this. Okay, so let's continue. We've got our new function, which is the old function squared, but we know it's going to be fine. So f of x equals x minus 1 squared plus root 2x minus 4 squared. Okay, so we're going to work with this new function where the derivative is easier to work with. Okay, now we need f prime, set it to 0, and we get our possible solutions. Okay, so the first one, easy stuff, just take the 2 down. Okay, next one, easy enough, just take the 2 down. Okay, I'm going to split this up a little bit, so it will be root 2 times root x. Okay, now by the chain rule, we need to do the derivative of this inside part. So the derivative of this, so this is going to be times root 2 over 2 root x. Right, because the half from here becomes minus half over here. Okay, and we want this to be equal to 0. Okay, solving this equation will then give us our critical points. Okay, or in this case, the turning points, because it's differentiable. Okay, any questions so far? All good. Okay, so let's carry on. Okay, a little bit of simplifying. We've got a 2 in front there, 2 over there. We can clean that up a bit there. So we've got root 2x minus 4, root 2 on the outside, root x. Okay. Okay, I've just simplified it a little bit. Now we need to solve for x. Okay, this fraction here, I don't want to work with that, so let's times the root x throughout. Okay, and then this root 2, I'm going to multiply inside as well. Next, I can distribute inside here. I can distribute in there and then simplify. Okay, so just multiplying out. Minus 2 root x plus 2 root x, we can cancel those. This 4 root 2, we can take over to that other side there. Okay, let's get rid of a factor of 2 there. Okay, now we've got this root, we don't want that. Let's square both sides. Okay, so on the one side there, we've got x squared and x, so x cubed. And then on the other side here, we're going to have 4 times 2, so that will be 8. Okay, very easy. We only get 2. Okay, so we get only one answer, so that must be the one we're looking for. If you had more than one answer, you would need to check. Right? So one of them would be a minimum, maybe one of them's a maximum. Here we just get one answer. Okay, so that's it. So x is 2, but remember we're looking for the point, not just the x value, we need the y value. Okay, so again, like I said last time, please no half answers. If you want to find the point, you need the x and the y. Okay, so we go right back to the top here. It must lie on the parabola. We know the x part is 2, so y squared is 4. Okay, we got a bit of a problem now. So if y squared is 4, we get 2 possibilities for y. It can be plus or minus. Okay, now we need to distinguish the two. Which one do we pick? Well, that's fine. We just go back to our picture that we drew. Y being plus 2 will be up here. Y being minus 2 will be down here. Which one's closer? The plus 2. So we take that one. You see why we draw the pictures. So 2, and then we take the plus 2, will be closest. Okay. So please don't leave your answer as plus or minus 2, because the minus 2 one, that will be much further away. We're looking for the closest one. All right. Any questions for this one? Okay. Okay. Now I need my notes back. Okay. Let's do the next one. No, before we get to the next one, some homework on this. Okay, so I'm going to draw the same diagram as before. So we have something like this. Okay, so exactly the same. Okay. So we've got this point here, 1, 4, and points here, 2, 2. Right, we know that now. Okay, so this is part 2. So for homework, please show that this line, let's call it PQ, this PQ line formed by the fixed point P and the point that we've just found Q, that line there, is normal to the curve. And by normal to the curve, we know that means at 90 degrees to the tangent. Okay, so for homework, show that or prove that the line PQ is 90 degrees to the tangent. Okay. And this will be true for any P. You can pick any P you like. So what this means is that the shortest distance between any point and a curve is normal to the curve. Okay. So you pick any curve, you pick any point, If you want to find the shortest distance from the point to the curve, it will be along the normal line. So knowing this now, it makes it a lot easier to solve other problems. Because if I give you a much more complicated curve, and I say find the shortest distance is equivalent to finding the normal line. And we know how to do that. So the shortest distance is the distance from P to Q along the normal. Yeah. Any questions for the homework? Okay. So for the homework, it's for this specific problem here, but it works for any curve. So any point, any curve, it works the same, but just do it for this example here. Okay. Any questions before we move on? No. Okay. Next problem. Determine the largest rectangle that can fit inside a unit semicircle. So that's our word problem. Again, here it's got largest, so it's an optimization problem where we want to maximize this rectangle. Okay, so step one, draw some pictures. We got ourselves a semicircle, and it says a unit semicircle, so that means the radius is 1. Okay. So in general, it will be some radius, r, but it's a unit semicircle, so radius 1. Okay. Now we want to maximize this rectangle here that will fit inside. So we can't draw it sticking out beyond the semicircle. It must be somewhere inside here. So I'm just going to draw a bunch of little pictures here just to show you the idea. If we try to draw something, let's say here, well, clearly we can do better than that. So if it's within the semicircle like this, well, we can always just move this point over here and make it larger. So the largest rectangle that we can fit must be touching the semicircle. If it's not touching, we can always extend it out so that it is touching. Okay, so that's number one. We can always draw it like that. And then number two, it could be like this. A very wide rectangle, but then it's going to be touching over here and over here. So the height will be small. So if it's wide, it will be short. And if it's very narrow, you see it will be very tall. Okay. So we need to figure out somewhere between these two is going to be our optimal rectangle. So what can we change? Between the green one and the pink one, what did we change? So what did I say? I said a wide one and a narrow one. I'm changing the base. Okay. So here I chose this base point. Let's call it X over here. And it gave me the green rectangle. If I choose this as my base point, it gives me the pink one. All we can do is change the base. The height is fixed. Okay. So I'm already going into step 2 with the labeling now. So let's call that X. So I choose x and the height is fixed. I can't change that. Okay, now we go into step 3, finding the function that we want to optimize and the constraints. And we've already said what the constraint was, right? The height is fixed. That's your constraint. So the area, right? Maximize the area, we get the biggest rectangle. It's just going to be based on height. So let's say that the height is y. If I chose this as x, on the opposite side, this will be minus x. So this whole base will be 2x. Good. And the height, we just call that y. Okay, that's the function we want to optimize. However, it's in 2 variables. Okay, we want to eliminate one of them. But we said earlier, when you pick an x, the height is fixed. Fixed means constraints. So y, in terms of x, we got that here. And we don't need to worry about plus or minus because we know y is positive. So we have our function, we have our constraints. We can substitute in and we get our function a of just x instead of x and y. Okay. Now we check, is there any problems with the derivative being undefined? No, everything's fine. Okay, differentiable. So we don't have to worry about those critical points in general. We just need to find the turning points. Okay. Again, always keep in mind that the function might look like this. And at this point, it's a maximum, but it's not a turning point. Okay, it's still a critical point, but it's not a turning point. Here we don't have that problem, so we can ignore this, but always keep this in mind. You might get something like that. Okay, so we just need to find the turning point. So a prime set to 0, we got our answer. Okay, we've got this in 2 parts now, so product rule. Okay, and then the next one, we need a bit of a chain rule. So it's going to be 1 over 2 root all of that. Okay, and then the derivative of the inside, that will just be minus 2x. We can put that at the top. Before we mess up with the factors here, 2 at the top, 2 at the bottom, we can get rid of that immediately. Okay, and then we want all of this set to 0. Okay, and then the plus and the minus, so let's put a minus here. And then x and x, that will be x squared. Okay. And then the 2. Okay, but now all of this is set to 0, so the 2's can go. Okay, and then we can take that one term over to the other side. Yeah. Now we have this root on both sides. We want to get rid of that. So let's multiply by this root on both sides. It will cancel this denominator and it will cancel that root. Okay, so we've cancelled the root there. Let's take the minus x squared over. Okay, so we've got 2x squared is 1. We can take the 2 over, take the roots, and then we're done. Now here we would get 2 answers, plus or minus. But again, we go back to our diagram. We put the x over here. So that will be the plus 1 over root 2. If you flip this over to this side, this will be the minus 1 over root 2. So we get both of these. Okay. But we've got our x value. Again, no half answers. We want the rectangle. So we need the height as well. So x squared plus y squared is 1. We can solve for y. Okay. So x squared, that will just be a half. Okay, so y is 1 over root 2. So the base is twice the x value, so 2 over root 2, and the height is 1 over root 2. So the max rectangle is 2 over root 2 along the bottom, and 1 over root 2 for the height. Okay, that will maximize that area. Okay. Any questions for this one? Okay. Pretty straightforward. Okay. Now we got a couple more geometric ones like this, a little bit more difficult. We're going to try to work through it together instead of me just giving the answer. But at each step, if you can answer it, you get some points. So it's going to be nice. Okay. Okay, so it starts off with the diagram. I'll give you the word problem, and then we'll go through through it step by step. Okay, so we've got this right angle triangle here. Y equals 3 minus 2x. Okay, so if I give you that straight line with a negative slope, that defines that triangle. Okay, so the base here is the x-axis, height there is the y-axis, and the hypotenuse is this line. Okay, but it's not the whole line. We cut it over here and over there. Okay, so that's our picture. So there we stop it, and there we stop it. So that will give us our height and our base. Next, somewhere inside this triangle, I'm going to draw a circle. Okay. So it's going to look something like this. Oops. Okay, so it must be inside. Something like that. Okay, there's a circle. Now I'm going to draw a couple more pictures. Okay, so the idea is to maximize the circle. What we can choose is where this point is. Okay, so we're going to move the circle somewhere in here. We want the maximum area. Now, just as a little side picture, if I move that point to the right, it must still be within the triangle. So it's going to look something like this. Right. If I move it to the right, it must still fit in that triangle. Okay, imagine this is in the triangle. We see that the area is smaller. Okay, so clearly that doesn't work. So somewhere between this point and this point is where the circle will have maximum area. That's what we need to find. Okay. And what defines the area of a circle? Pi r squared. We need the radius. So we need to find the center, and there's going to be some radius, r, that will then maximize it. That's the goal. Now, that's the question. Now it's up to you. Okay, I'm not going to do anything more than ask you, step 1, step 2, step 3. Okay. So step 1, that's done. We've already drawn the pictures. We've got the problem. Now we need to do step 2, label. So we've got the radius. That's fine. What else can we label? Remember, the more stuff you label, the more stuff you have to work with. So if you just leave it at the radius, you're kind of stuck. So what else can we do? Exactly. So the height of the triangle will be
1.
1.
1.
3. 1 to 7. 3. Okay. What about the base? 3 over 2. Good. Okay, the radius we don't know, so we're going to leave it like that. What about the center point? The center over here. We don't know what that is, right? It can be any xy. We don't know. Okay, so the center point is some there. That horizontal dotted line, that will be x away. And that vertical dotted line there, that will be y. Okay, to give us the center. Okay. So that's labeling done. The next is to figure out the function that we want to maximize and constraints. Let's start off with the constraints. Okay. What is the main constraint for this picture? Okay. Okay, so we need some sort of equations to describe it. Right, like before, we could write this constraint like this, right? So the rectangle must fit in the semicircle, which means its height must be this y value here. Okay. So here we've got a similar thing. The circle now must fit in the triangle. But what is the constraint on, let's say, the radius? So this radius here, there's a constraint to it. It can't be too large, otherwise it's outside it. So what is stopping it going out? The hypotenuse, exactly. From here to here, that's the largest it can go, the radius. Yeah. So this radius line from the center to the hypotenuse is the maximum it can go. The maximum it can go. That gives us our constraints on the radius, and that will tell us how large the circle can be. So the distance from xy, so that's the center, xy, to the hypotenuse, that limits the radius. So that will give us the maximum possibility. So the distance from xy to the hypotenuse limits or constrains, however you want to say it, the radius. Yep. So if we find the maximum possible distance, that will give us the maximum possible radius, which will give us the maximum possible area. Make sense? Yeah. So let's redraw this diagram a little bit bigger so we can draw some more lines. So we got something like this. We've got the circle. Remember, we want the largest possible circle, so it must touch at all these points, right? Same as the rectangle. If it's not touching this point, then it's smaller. Over here, we've already worked that out. If it's not touching this point, it's going to be smaller. Same thing there. It must be touching there. Okay, so we've worked that out already. And then somewhere